Hi guys.
Hey.
Hey guys. Hey. This is gonna be quick. This is gonna be quick. Because I want to play League of Legends with my friends. Um. So today, on my lunch break at work, of course, oh, not the C1. Buy it in paperback. Maybe. Paperback, 27.60. Good. Anyway, let's not get distracted. Beej's Guide to Network Concepts. What is examples to download? IP routing demo. Nah. HTML. So I finished the Better web server yesterday on stream, and then on my break today, I was reading this chapter about endianness and integers. Let's see if I can recall any of this. So, yeah, it starts with the integer representations. So it's talking about how with 1 byte you can represent 255, and then with a second set of 8 bytes you can represent another 255 numbers. But if you put a key realization here is that you can put sort of 2 bytes next to each other, and the this is the example. So you can put two of these bytes next to each other, and you're able to encode, obviously, just like increasingly large numbers, because with every combination across these 8 bits, you're afforded a larger number. But the realization here, or not realization, but this just works nicely. This works just as well between binary representations of like decimal numbers, as well as hexadecimal byte representations. So, in 111111111 is 255. Add one to that, you need a second byte to represent 256, where this one's represents 2 to the 8, 9. But just as, oh jeez. We can do the same thing with hexadecimal. In this case, that's of course like base 16, 0 to 9, and then A to F. So with the way we can do that, like with a number like this, what this actually means is 1 times, we could think of it instead as a power of 2. We can also just think of it as 1 times 256. 1 times 256 plus whatever's in this byte. So plus 1, and that's 257. 1 times 256 plus 2 to get 258. So you can do the same thing with hexadecimal. So we can represent, for example, 259, because 0, 1, this is 1 times 256 plus 3, giving you 259. This is 3 in hex, and then this is 1 in hex as well. But this byte, it's nice, right? Nicely, you've got 8 bits in a byte, or 2 hex bits. I don't know what you call that in a byte. No. Anyways, this property of just being able to add more and more bytes in sequence like that to encode larger and larger numbers is the same for binary and hex encodings of the decimal number. But then endianness refers to, I guess, the fact that in some architectures you can, as you would intuitively do it in what we call big endianness, is when you have the largest bit leading. And this is how we count in decimal anyways. Whereas in little endian architectures, the smallest bit is actually the leftmost. So it gives this example. This is analogous to me saying I want 123 pieces of toast, when in fact I really want 321. And that might seem really stupid, but actually, little endian representations of byte sequences are the meta, actually, as far as like Apple and Intel, like CPUs and other like chip architectures and stuff go. And that's because, well, it's for a few reasons. The key performance advantage up front is that you have immediate access to the smallest bits. So say you're like incrementing a counter by 1, but what you're incrementing, or not a counter, say you're incrementing something by 1, what you're incrementing is this like really long address. Instead of having to basically like read through the entire representation of that address, you already have this like little thing up front that you can edit. And I guess that's just because for like most operations in these architectures, like you're doing stuff to the smallest bit more often than you're addressing sort of like the second byte or the third byte. More often than not, we're just like shifting bits around by 1 in either direction or whatever. So that's like the performance advantage, but the like historical context I think for this is that like when they were designing these architectures way back in the day, like, you know, when they're coming up with their little adders and like key CPU instructions, they're like very mindful of just how restricted, like just how little computing power they have. And I guess they just sort of had a good understanding of the fact that they would be, again, having to do these little operations on the littlest things more often than they'd have to do them on the bigger sides of these same representations of addresses and stuff. So yeah, like it's a convention that comes out of the sort of historical context of like not having a lot of resources to do this stuff. But network programming is done with big endian encodings. And it's called network byte order in that context for some reason. And then it just talked about how using the Python socket or not even socket API, just Python standard library, we have a 2 bytes method and a from bytes method, and that allows you to specify either big or little endianness when you're encoding from say decimal to bytes. So yeah, with 2 bytes, you give it, you call it, you have some object, like you have a number here, 3490, and these objects have a dot method to convert them to bytes, which is, and then you give it how many bytes you want to use to represent that number. So, yeah, how many bytes you want to represent that number. Of course, yeah, so like with 1 byte, you're able to represent up to 255, 2 bytes, 65,000 or something. Whatever 2 to the 16 is. 65,000 bytes! And then you specify the endianness of that. I made this mistake. Oh, and then it works correspondingly with hex stuff. If instead of representing it n, which we have as 3.90 here, you can represent it in hex as so, and call the 2 bytes method in the same way. To convert bytes back to a number, we have to take a byte format of a number. You call from bytes on it. But sorry, instead of calling it on it like we did with 2 bytes as like a dot method, you're using the int object from bytes method to turn it, and then you pass it the thing, the number, and you specify the endianness. And then there's just this little section to reflect on the work you did. By the time I explain everything I did today, I'm not even gonna have time to keep streaming. And then there was this chapter I did today, which was about parsing packets. And where did this go? This basically, so this just gave some like pseudocode about how we could more mindfully on a socket be listening for like a continuous stream of bytes, instead of having to rely on like specifying like an expected number of bytes to receive. This pseudocode uses like a buffer. So to go through the examples I give, you've got like a buffer going, and okay, so the sentence example is what they give here. You've got this function you've got the function listening. So you have to call this the same socket receive method, and you specify the number of bytes you're trying to receive. And you're waiting until you find like a period, I guess. And when you do find a period, you so as you're receiving this stuff, you're appending it to the buffer. Once you do find the period, you're returning that thing and popping it from the buffer, and then you continue on with that unfinished sentence until you find its period or whatever. Yes, I think I'm gonna have to come back to this chapter, I think, for the 2 chapters from now. So this next chapter, Atomic Time, I did this project today. It was very quick. The task was to basically set up a simple client, like write a simple socket to ask the National Institute of Standards and Technology for the official time that they serve on their server. And they've got this public facing server that any client in the world is allowed to ping once every 4 seconds, and it returns the exact number of seconds since January 1st, 1900. And the task was to write a socket to ask this server for that time, and then on the other side to ask your actual computer to do the same thing, to tell you its clock's time from that same start date, and to compare them. And mine ended up being exactly the same, which is good and expected. I mean, I'm on a very common CPU architecture. I'm on a Mac. I mean, if these weren't aligned, that would be concerning. So it was pretty straightforward. That just entailed, let's see if I can find it. So yeah, you spin up a socket, you define a port. It's on port 37. I forget what the actual port number is, but I remember reading that there are there are port numbers set aside for like specific things that you can't touch in some of these other like client server projects, and it's all ports under a certain number, and 37 is well within that. So I mean, that was just cool to see that now. and then I give it the address, which is time.nist.gov. And then you use the connect method on the socket. You give it the tuple with the address and the port, and uh, you would normally have a loop here that is using the receive method and repeatedly asking for like a certain number of bytes. But because we know the exact size of the payload that this server returns, I didn't use a loop. I straight up connect that tuple, and I just straight up receive an explicit number of bytes, which is 4096, and um, that comes to like in byte form. Uh, so we call the int dot like from bytes, and we give it that um, variable we're using to store the response, and we specify the endianness big, and we close the socket, and from there you can print it. I also just call uh, the like Unix epoch time function that comes in the pseudocode here, and I print them both, and they're the same number. Yeah. So I'm not starting this tonight, but it's good to. I wanted to review what I had done already. So yeah, I guess this project will be. This will be implementing the stuff from 2 chapters ago about having the buffer and parsing out a period and therefore popping that thing from the buffer and returning it. Yeah, I'm not up for this. It's too late. This is gonna be hard. I just know it's gonna take me a while and shit. But I can. I can do those emails I wanted to. So I'll go point one. Information works out. You're just volunteer. We have many wonderful for the church. Small. I've reached out to a project. Apply. So 7, 8, minus 3 is 5. After 5 p.m. 8. o'clock. Five 15. Or 12. Also available on Wednesday. On Wednesday. 3:30, probably leave at 1. Also on Wednesday. Please let me know if please let me know if that works for you. I hope you have a great day. Eli James. I'm also in the morning, so I try to let me know if that works for you. I hope you have a great day. Alright. Oh, dude, let's fucking go! Alright. Goodbye, wife. I'm gonna go play a video game and then come to bed. See you.